from the start. Baby, when you broke my heart, that I had to come again and show you that I win. Your love of mine.
Hi everyone, and welcome to another 861 video. For this video, I'm going to be focusing on both logistic regression analysis in practice and multinomial logistic regression analysis in practice. So this video is kind of going to cover basically weeks 7 through 9 material. I'll start first with talking about logistic regression. We use logistic regression when we have a binary dependent variable. And so if we're using SPSS or basically any other software program, we're going to let 1 equal our category of interest and 0 equal our reference category. So usually 1 is where like the event did occur and 0 would be where the event did not occur. One of the assumptions of logistic regression analysis is that you have exhaustive categories. So it shouldn't be possible to be both 0 and 1, and it shouldn't be possible to be neither 0 nor 1 when you're coding this particular variable. Logistic regression analysis helps us estimate the odds of an event actually occurring. Commonly in criminology and forensic psychology, we might be looking at something like recidivism, but we could also look at something like whether an individual has carried a gun in the past or whether an individual is involved in a gang or not. But we know that since we have this 0-1 outcome, we can't really look at change in that outcome because 0 and 1 is only a 1 unit change. So instead we transform our DV to be able to look at the log odds of the DV, so not the change in the dependent variable itself. We have to do this because there's only that 1 unit change in the dependent variable. Only 1 change is possible. So we create this log odds S-curve that allows us to look at kind of like the probability distribution of the event happening or not happening. Logistic regression is quite convenient because several of the assumptions of ordinary least squares do not actually apply. So we don't have to worry about a normally distributed dependent variable, nor do we have to worry about normally distributed independent variables. We don't have to address the assumption of linearity between the raw values of the independent variable and dependent variable, but we do have to assess linearity between our interval level independent variable and the log odds of the dependent variable. We can forget about the assumption of homoscedasticity when it comes to logistic regression, and we don't have to worry about the normal distribution of our residuals either. Relative to OLS, there are not as many assumptions in logistic regression analysis. There are really only 3 main assumptions that we need to address post-analysis. Pre-analysis, we have kind of all the same assumptions that we've talked about in this class so far. So your dependent variable has to have a meaningful coding strategy. So you should have an exhaustive and categorical dependent variable. You should be in your model including relevant variables so you can meet that best linear unbiased estimate assumption. We want to have that appropriate sample size, so that appropriate cases to variables ratio of about 15:1, and we want to have independent observations on our dependent variable. For example, we would want to make sure that an individual that was let's say we're looking at gang membership as a dependent variable, whether one person is a gang member or not should not impact whether another person is a gang member or not. So one individual's score on the dependent variable shouldn't impact another individual's score on the dependent variable. Post-analysis assumptions, as I mentioned, one is that linear relationship between the interval IVs and the log odds of the logit transformation of the dependent variable. Just like in linear regression, or OLS, you do not need to worry about a linear relationship between your categorical variables and your dependent variable. Another post-analysis assumption that we need to check is the assumption that there are no outliers. And we're not talking about outliers such as extreme values of our dependent variable, because as we know, our dependent variable can only equal 0 or 1. So when we're talking about outliers in this case, we're actually talking about residuals. If our actual value for a given case on the dependent variable is 1, so an individual is a gang member, but their predicted probability of being a gang member is extremely low, like 0.05, SPSS, or your logistic regression analysis, might identify that as an outlier because our prediction was really far off. So the residual value was large. The residual itself was an outlier. We are also concerned with the assumption of multicollinearity. So again, that's the interrelationships or the correlations between our independent variables in the model. And at least in SPSS, we can't directly address that question of multicollinearity when we run our logistic regression analysis. So the solution is just to run the exact same model, but using linear regression. And then we can interpret the linear regression output to see if our variance inflation values are an issue. As always, before we're running our analysis, we need to make sure that we understand our data at especially the univariate level. So we need to make sure that our dependent variable is coded as either 0 or 1. And we should be running descriptive statistics on this variable to examine the distribution. So what percent of the sample equaled 0 and what percent of the sample equaled 1. We'll kind of explain this further in the analysis or when I go through a logistic regression analysis example, but generally speaking, it's ideal if our dependent variable is equally split between the no's and the yeses, or the zeros and the ones. For the purposes of this class, you probably want no more than a 90-10 split between your 0-1 or your 1-0 either way. In certain circumstances, we would do what's called a rare events logistic regression analysis. This is really only reserved for when we have particularly large samples, but less than 1% of all cases are indicating 0 or indicating 1. So for example, if we were looking at population data on early mortality, say mortality before the age of 30, especially in Western industrialized nations, is probably relatively rare. So we would need to do a rare events logistic regression analysis if we wanted to do some type of logistic regression analysis. When it comes to our independent variables, running logistic regression analysis is much easier than running linear regression analysis. This is because logistic regression analysis can handle nominal and categorical variables with any number of different categories. For example, in linear regression, we have to do that G-1 rule if we were looking at like ethnicity with 3 different ethnic groups. We don't have to abide by that rule. We don't have to create multiple dichotomous variables in logistic regression. We just enter that variable as a categorical variable, and then in SPSS we can tell SPSS that this is supposed to be a categorical variable. Then we can also tell SPSS what we want the reference category to be. In our discussion of linear regression, we looked at the different ways of interpreting the B coefficient versus our beta coefficient, so unstandardized B versus standardized beta. In logistic regression, we do technically get a B coefficient or a B value, but we don't really have as much of an interest in interpreting this coefficient because it's just basically talking about a unit change in the log odds of our dependent variable, which isn't very interpretable. But logistic regression has another coefficient that we can interpret, which is called an odds ratio. How we interpret an odds ratio depends on, first, the level of measurement of the independent variable, whether it's, for example, an interval level variable or a categorical variable, and then whether that odds ratio is greater than or equal to 1 or less than 1. And at the end of the video, I'll provide a little bit of extra information on interpretation, go through some extra examples if students are still having a difficult time with it. For today's class, I'll do an example of logistic regression analysis using data from the Pathways to Desistance study, where we're going to be looking at gun carrying as our outcome of interest. Gun carrying is coded as 0, where they have never used a gun or carried a gun in the past, and 1 is coded as if, yes, they have carried a gun in the past. So that will be our dependent variable, and we'll be looking at 2 main independent variables. The first is an interval level measure of features of psychopathy based on the PCLYV. The second is a dichotomous measure of gang membership, 0 being no, 1 being yes, and we'll control for gender and demographic characteristics in this analysis. So now I'll actually just jump into SPSS and I'll show you, I'll take you through the different steps that we follow to make sure that we get the right output, that we address assumptions, and so on. So I'm going to run through with you an example of logistic regression. So this is using, again, the Pathways to Desistance study data set. Our main independent variables that we're interested in are the PCLYV total score, so it's an interval level variable, and then history of gang involvement, which is a dichotomous variable, and then we are going to control for a person's gender and ethnicity. We also have here our dependent variable, our dichotomous dependent variable, which is measuring the history of carrying a gun in the past. If we have a look, we can see that we have about 50% of individuals that said no, they've never carried a gun ever, and then about, again, 47.2% of individuals that said yes, they have carried a gun in their life's history. As we're going to see through the analysis, having a dichotomous dependent variable that's basically split 50-50 helps us with classification accuracy. So that might not mean much now, but just keep this in mind as we move through the example. So we're going to run our logistic regression analysis by going to Analyze Regression, and we'll select Binary Logistic. And then it is very, very simple. We're just going to enter that gun carrying variable in as our dependent variable, and we'll have our different independent variables entered under the covariates box. And as I mentioned, we have three categorical variables. We have ethnicity, gender, and gang involvement. We're going to go to categorical, and then we have to basically identify which of the variables in our analysis are categorical. So we highlight everything but PCL and we enter them into this box here. And then we have the option of identifying what we want the reference category to be. For our dichotomous variables, it's very easy. We have for gender, you can see that 2 equals that they're a female participant and 1 equals that they're a male participant. So in this case, for gender, we have our reference category as last. So this means that we'll be comparing males against female participants being our reference category. But if we wanted to change it up, we could make the first category, we could make males our comparison group. We'll leave it as is for now. For gang involvement, right now we have gang involvement yes as our reference category, because gang involvement is coded 0-1, where 0 equals not gang involved, 1 equals gang involved. So if I want non-gang involvement to be my reference category, I can go down here, select first, and then very importantly, make sure you hit change. And as you can see here now, we're going to have the first category of our categorical variable be our reference category. So now I'll be comparing gang members to non-gang members. Here we're comparing male participants to female participants. And here we have, and you'll always know, see how it says first here, but not first up here? This means that it's still set to the default setting, meaning that it's our last category of interest. So in this case, I believe that Hispanic participants were our group number 3. We can just double check that here. Black was 2, Hispanic is 3. Yes, if you have a categorical variable with 3 or more categories, you still only have the option of setting that first category or the last category as your reference group. So I have in this instance, Black participants, their value was 2. If I wanted Black participants to be my reference category, I would have to manually recode or transform that ethnicity variable so that Black participants were either the first category in the categorical variable or the last category, the last highest value of that categorical variable. So we're all okay now. Again, we're just going to be looking at, in this case, Hispanic is our reference category, female participants are our reference category, and non-gang involved participants are our reference category. So we're all good. We can hit continue, and then we'll just check out options. And for options, we want to select classification plots. It's going to give us an indication of our classification accuracy. We can select Hosmer-Lemeshow's goodness of fit test, and this is going to tell us about whether our observed and expected values differ across our 10 deciles. So what I mean by that is, remember, the Hosmer-Lemeshow test takes our entire sample, divides it into relatively equal groups, 10 relatively equal groups, and examines whether the predicted values from our main model are similar to our predicted values for our little decile sample. So the predicted values from our main model are what we expected to find, and then our predicted values from our subsample model are what we actually observed. So we're looking for a discrepancy. In fact, we don't want to see that discrepancy. If we do see that difference, then it's suggesting that we have poor model fit. Our model is misspecified. What we're also going to want to select is our confidence interval for our exponentiated b, or our odds ratio. Really wide confidence intervals would suggest that we should have less confidence that our odds ratio value that's given is the actual value that we would observe in our population of interest. We can also select our case-wise listing residuals. This is going to be detecting outliers, but remember, it's not outliers in the sense of extreme values. It's outliers in the sense of extreme residuals, aka extreme error. I didn't mention it, but just like linear regression, we can also run different blocks. So we can do what's called hierarchical or sequential regression. If we were interested in looking at demographic characteristics as our first block, we would just keep these two demographic characteristics in, select next, and then we would add in our two variables of interest. We are also going to go to save, and there's a couple of things that we're going to be interested in. One is relating to residuals, so we're going to select unstandardized residuals and studentized residuals. Then we also want predicted probabilities. This is going to be useful for calculating our AUC values. So now we can hit continue, and then we can paste our syntax so that we can have a copy handy, and then we can just hit play, and then we're going to bring up our output. The first thing that you'll notice is the percent of missing cases in our sample. So here we can see 8.9% of our data are missing, which is okay for the purposes of this example. Our beginning block, block 0, is basically just looking at our model if there were no actual independent variables entered into the analysis. And what we're interested in here is our classification accuracy. So it's showing that if we just guessed the most common category of our dichotomous dependent variable, how often would we be accurate? And this is what was really important in understanding why a 50-50 split is useful. Our analysis is going to be comparing our beginning block to our block with variables entered. And we're going to be looking for improvements in classification accuracy. Imagine if gun carrying was no equals 80% and yes equals 20%. So this means that without any variables entered into the analysis, if we just guess no every single time, we will have an 80% classification accuracy. So now try to think about how we would improve upon that model. So we can only improve by a total of 20% because we can't go beyond 100. In fact, it's very likely that we would ever reach 100%. If we are at 50-50, that means we have 50% to grow. So you will notice that 53.4% is actually a little bit different from what the distribution of our gun carrying variable is. Here we can see that it's actually 52.8%. The reason why we see this discrepancy is because we lost participants due to list-wise deletion because of missing data. One of the next steps that we're going to do, and I'm just going to go through it in order in which the output appear, is have a look at our omnibus test of model coefficients. Here we want it to be significant, and in fact it is. The next thing that we'll be looking at is our model summary, and you know how I feel about pseudo r-squared values. You can take a look at Nagelkirche r-squared, report one of the two. I'll go with Nagelkirche because I think it's a little bit more common. We can see that that r-square value is 0.329. Whatever you do, do not interpret this as explained variance. You could look at past literature to see what other Nagelkirche r-square values were, and you could compare your value to past research. Generally speaking, I would just report this either in the table or in the text and move on. You don't need to say too much about it. I kind of just put it in there because it appeases reviewers. The problem that we have that we're going to have to address at some point is that we have a significant Hosmer-Lemmerschau test. What this means is that our model is misspecified. If we look down here, we can see our 10 deciles or 10 subgroups, and we can see the number of participants in each subgroup. So we have 121 participants here, and within this random subsample, we had 116 who were observed to say no to gun carrying, and 5 who were observed to say yes to gun carrying. And this expected value shows what we would have expected the percent of individuals or the number of individuals to be non-gun carriers were, and the same thing for those that did carry guns. So we're looking basically within the no's and within the yeses, the degree of difference between observed and expected values. And of course, you don't need to calculate it on your own. This is just that simple chi-square analysis. Remember, back to week 2, we were talking about observed versus expected values. I'll come back to why this might be significant later on in the class. Here we have our classification table that's showing our improvement in classification once we've added in our different variables. So here we can see that percent correctly classified is 69.9%. Our previous model with no variables entered in was about 53.4%. So we've seen about a 15% improvement in model fit. Whether that is a significant or substantive improvement is really something for you to judge. This is why I kind of prefer AUC values to our classification table, because we have those past benchmarks in the prior literature to tell us whether our sensitivity and specificity of the model is substantial or not. So on that note, before we check out the variables and the equation, let's check out how we calculate our AUC values, because it's not something that logistic regression automatically gives us. So remember when we clicked save, what that in the logistic regression dialog box, we went up to regression, then we went to binary logistic, and then under save, we selected our predicted values probabilities. That gives us this variable here. What we are going to do is we're going to enter this into a ROC curve analysis, but before I do that, I'll just step out of SPSS and explain to you a little bit more what AUC values actually are. AUC values measure the area underneath the ROC curve. So the ROC curve gives us this curved line on a scale of probabilities from 0 to 1, and the area under the curve basically tells us our model's accuracy, and it bases the accuracy according to the balance of sensitivity and specificity. Sensitivity tells us the true positive rate. We predict the event to happen, so we predicted 1. And for our observed case, it actually indeed was 1. On the other hand, specificity is the true negative rate. So we predicted the event to not happen, aka 0, and indeed the event did not happen or was 0 for that particular case. If we do 1 minus specificity, that gives us the false negative rate, where we predicted the event to not happen, but it actually did in fact happen. So the AUC ROC indicates how well the model is adept at distinguishing between groups. So it's not just looking at how well we can predict the outcome of interest occurring, or how well we can predict the event to happen, but also how well can we predict the event to not happen. Because if you think about it, it would be easily to perfectly predict whether or not the event happens. I would just guess 1 every single time. And even if the event only occurred 25% of the time, if I guess 1 every single time, then the sensitivity will be perfect. I will be perfectly sensitive, but I will lack specificity. So we want our models to find that balance where we're able to predict basically equally both the 1s and the 0s. When it comes to the actual AUC value, there are differences of opinion in terms of the magnitude of these values and how to interpret them. Harris and Rice are forensic psychologists, and so these are the benchmarks that maybe I'll see more commonly in criminology and psychology. Garson's benchmarks are a little bit more conservative, which is to say that you need a higher AUC value to meet those different benchmarks. I kind of like Garson's approach of being a little bit more conservative, but I think in the social sciences, at least in Crim and Psych, you're more likely to see the Harris and Rice benchmarks used. What Harris and Rice say is that if it's a value that's less than 0.556, it's essentially a trivial or non-substantial effect size. If it's 0.556 but less than 0.639, it's a small effect size. If it's 0.639 but less than 0.714, it's a moderate effect size. And anything from 0.714 and above would be considered a large effect size. I'll post to Canvas an article that's helpful for further understanding AUC values. So this predicted probability is a term I haven't really yet introduced. Essentially, when we run our logistic regression analysis, we're able to save for each case or each participant that we have in our analysis the predicted probability that their true score was 1. So remember, just like observed and expected values that we've been talking about for forever in this class, if 1 is the observed value for a given individual and 0 is the observed value for another individual, what is the probability if we randomly drew a 1 and a 0? We would get that individual that scored a 1 would have a higher predicted probability, a value closer to 1, than the individual who scored a 0 or whose observed value was a 0. That doesn't make a lot of sense just yet. Don't worry, we'll do another example where you'll be able to see it in SPSS. And in fact, actually, I'll just go through that analysis with you now. Okay, so now that we have a little bit of a better understanding of what AUC values and the ROC curve actually are, we're going to show you how to actually calculate the ROC curve and get your AUC values. Now this tripped me up a little bit because SPSS has actually changed. It's going to depend on which version you're using, but we're going to go up to Analyze. For some versions, you'll see the ROC curve right down here is its own analysis. For other versions, you're going to have to go to Classify, and then you're going to go up to ROC curve. And we're going to have to enter two key things. So we're going to enter as our test variable, our predicted probabilities right here, and our state variable is our dependent variable. So just our gun carrying measure here. And the value of our state variable is going to be 1, where 1 equals yes, the event did occur. We can calculate the ROC curve with a diagonal reference line. Then we want the standard error and the confidence interval, and we're going to hit OK. And then we get this nice graph here, and it's going to tell us the area under the curve that's explained by our analyses, which we can see is 0.794. So if we go back to the benchmarks developed by Harris and Rice, we can say that we actually have a relatively large effect size here, and that it is significant. We can see that the confidence interval isn't too large. The lower bound and upper bound are fairly close to one another. If the confidence interval was actually quite wide, when we looked at this ROC curve, instead of seeing this relatively smooth line, we would probably see somewhat of a staircase shape to the curve. Usually it's an indication of an issue with sample size. So what would you report when you are writing up this information? So you would say that the AUC value equaled 0.794, and then you could write P less than 0.001. Of course, as I mentioned, I think in the lecture, Garson says, I don't know about those Harris and Rice benchmarks and had a little bit more conservative benchmark. So in this case, if we were based on Garson, we would say that it's like an acceptable area under the curve value. Just keep in mind that the magnitude varies depending on the type of discipline that you are in. If we were focusing on things like the survival probability for a new medication or a new type of surgery, we would probably want our AUC value to be much, much higher, because we don't really want to be trying these sort of like experimental surgeries if we have somewhat of a low AUC value in prior sort of tests of the actual procedure. One thing that I haven't gone over, but Garson went over it, so maybe students will be interested in this. It's another way of looking at model accuracy by plotting our predicted values against our standard residuals. So I'll show you what I mean by this. It's very simple. We're just going to go up to Graphs, Legacy Dialog, and we'll go down to Scatter Dot, do another simple scatter graph. So our standard residuals is just, again, our degree of error. We got this by going into logistic regression, and when we saved, we had that option of saving residuals. And then we're going to be plotting this against the predicted probabilities, which again we got from that exact same place in the save dialog box. So in this case, standard residuals are going to go on our y-axis, and we're going to place our predicted probabilities on the x-axis. And we can hit OK. And then we're going to get a graph that looks like this. And for like visualization's sake, we might want to create two lines to sort of split up the graph. So if we double click on the graph, you can start by going to the reference line for the x-axis. And basically that 0.5 probability, predicted probability, would mean that the model had no idea whether the individual was a gun carrier or not a gun carrier. The lower the predicted probability, the more confident the model was that they were not a gun carrier, and the higher the predicted probability, the more confident the model was that the individual was a gun carrier. So we can change the line a little bit to make it a little bit more standing out. Hit OK or apply and then close. And we can do the exact same thing with the y-axis. So here, sometimes it will set the position to be something different. I always want it to be set to 0. What does 0 mean? 0 means perfect prediction. So it's our standard residual. And if our residual is 0, it means we had no error. So we're going to look at the discrepancy kind of below or above the error. We can go to lines again. We can change the weight to 2, make it red, hit apply, close, and now we have this graph that we can take a look at. What we want to see is ideally we would have two lines. One would be where we had all of our cluster of individuals who did not carry guns, and in fact the residual was very low, so it'd all be clustering here. And then the same thing over here where we had a very high predicted probability but very low residuals. So basically we just want to see dots as close as possible to this horizontal line. On the right side of the vertical line, we're seeing where the model felt that the individual was actually involved in gun carrying. That's their predicted probability, and to the left it's where the model did not predict them to be a gun carrier. So why are there two lines, you might be asking? The bottom line is for individuals who were not gun carriers, and the top line is for individuals that were gun carriers. So here we can see these individuals were gun carriers, and they had a high probability of being gun carriers, so the standard residual is low. Here they were gun carriers, but their predicted probability of being a gun carrier was very low. And so we have a high residual, high degree of error. Now that we have checked out the overall efficacy of the model, we can begin to interpret different variables that are actually in the analysis. And here's where we need to have kind of that good memory of what we kept in as our reference category. See in the ethnicity variable how we have this little 1 in bracket. This indicates the first category being interpreted and not what was coded as a 1. So recall 1 equaled white. This doesn't mean that 1 equals white. This means that this is the first category of interest. White was our reference category. So in this case, this is black compared to white participants, and this is Hispanic compared to white participants. We can see here with our B coefficient that it's negative. So we would talk about the logged odds, average logged odds difference between black participants compared to white participants. So in this case, it's negative. That means that there's a lower odds for black participants compared to white participants, but doesn't tell us what that odds actually is. So this is where we can look at our exponentiated B value or our odds ratio, and it's 0.573. Whenever you have a value less than 1, it means that the outcome of interest, in this case gun carrying, was less likely to happen for your category of interest, so black participants, compared to white participants. But we have to do a bit of a transformation before we can actually interpret what's going on here. We cannot look at this and say, okay, 0.57, does that mean like a 0.57 less odds? That's not how we interpret it. If we want to continue on with our comparison of black participants compared to white participants, keeping white participants as our reference category, all we have to do is do 1 minus the actual odds ratio, so 1 minus 0.573, and we get 0.427. What we can do now is convert this into a percentage. So we could say that compared to white participants, black participants were 42.7% less likely to carry a gun. We could also do one other thing. Let's say if you didn't want to know about less than, let's say you wanted to know about more than or increase the odds. What you would do is you take 1, instead of minusing, you would divide by 0.573. What this does is it gives you an odds ratio while also switching your reference category and your category of interest. So in this case, white participants becomes our category of interest and black participants become our reference category. So we could then say that white participants were 1.75 times more likely to carry a gun compared to black participants. So really it's your choice. Only bother doing one of those two approaches. You can do either 1 minus, you keep your reference category is the same and your group of interest is the same. You're just interpreting it now as a lower odds. If you'd rather like interpreting it as a higher odds, you need to change your reference category and your group of interest. And all you have to do here to do that is do 1 divided by your odds ratio. Now we can begin to look next at our next significant variable, which is gender. We have to again keep in mind what our reference category was. Here we were comparing male participants as our group of interest to female participants, and we can say that male participants were 4.16 times more likely to carry a gun compared to female participants. Or we could say that male participants were 416% more likely to carry a gun compared to female participants. Now we have PCL total score, and so we're going to do something a little bit different because this is an interval level variable. So we can see that it's 1.12 is its odds ratio. So we would say that a 1 unit increase in PCL-YV total score increased the odds of carrying a gun by a factor of 1.12, or increase the odds by 112%. Either or, both are correct. Last example here, gang members, where once again we had gang member as our group of interest being compared to a non-gang member. We can say that gang members were 364% more likely to have a history of gun carrying compared to non-gang members. Or we could say that gang members were 3.64 times more likely to have carried a gun in their past compared to non-gang members. The number one thing to remember is that you need to keep track of what your reference category is, so you're always interpreting in the right way. And just one of the ways to notice if something weird is going on is if your odds ratio doesn't make sense. So if my odds ratio for gang membership here was less than 1, but I was interpreting it as gang members was my group of interest, then I might want to step back and say, does this make sense? Why would gang members be less likely to be carrying a gun in their history compared to non-gang members? So that's just like use theory to recognize whether maybe the odds ratio isn't making sense to you, and think about, is it not making sense because I have misremembered what my reference category actually is? You don't need to worry about interpreting non-significant variables. I will go through at the end of the lecture today just some more examples about how to go about interpreting odds ratios. I'll hop out of SPSS again to talk a little bit about some subjective language that can often be used when we're looking at an odds ratio. Students will want to know, what is a large effect size? What makes it a big odds ratio? And I actually think that we should avoid this sort of subjective language and not really worry about these benchmarks, especially because the size of the odds ratio can really be dependent on a lot of things. If we're looking at an interval level variable with a really wide range, then it's hard to have an odds ratio that's particularly high in magnitude. Chin, in the 2000 paper, basically said that if you have an odds ratio of 1.20, it should be interpreted as small, 1.72 as moderate, and 2.40 as large. And I kind of disagree with this, because what can happen is if we don't pay attention to the confidence interval, we can overstate the size or the magnitude of our odds ratio, especially if we have relatively rare events as our independent variable or dependent variable. What can happen is that we will have a large odds ratio, but also a really wide 95% confidence interval. So maybe our odds ratio is 15, but our confidence interval ranges from 1.56 to 57.42. So we have no real confidence that our true value of that odds ratio is 18. It really varies. So I would say avoid using the subjective language when interpreting your odds ratio, or at least keep in mind what your confidence interval is. And if you have a really wide confidence interval, then maybe don't be too strong in your assertion about it being a big or a large effect size. Okay, so obviously we should be doing this before we interpret our analyses, but I just wanted to get the interpretation out of the way and sort of follow the flow of the SPSS output. At the very end of the SPSS output, we get to our outliers. So remember when we went up to analyze and we went to regression, binary logistic, and we were able to, under options, save all outliers that were outside 2 standard deviations. So here it will show us with cases with studentized residuals greater than 2, so 2 standard deviations above the mean in this case. And it will give us a list of all the individuals in the sample that had that residual of greater than 2. And so that case of 64 will identify the 64th person in the data set. What I've done is just identify them and put them right at the top here, so it's nice and easy to see. So this person had that 2.23 residual, and we can see here that they were a female participant, yet they were a gun carrier. So this is why we're seeing this basically discrepancy. So we can actually see the residual value here of 0.916 and their predicted probability here. So basically they were predicted to be a no, a very low probability of being a yes, yet they were a yes. So 1 minus 0.08379 is our residual value here. So they did carry a gun, yet they were a female participant. They had a PCL-YV score that was lower than average. The average PCL score was about 15 something. This was 14. So they were, PCL scores were supposed to increase the odds of gun carrying, yet this person had a lower PCL score, yet was a gun carrier. And same thing with gang involvement. They were not a gang member, so according to our model's prediction, they should be at a lower probability of being a gun carrier, but again, they were a gun carrier. So basically that's all the residual is looking at. It's looking at, well, we expected this type of person to be not a gun carrier, but in fact they were. Another assumption that we need to look at is, remember that we violated that Hosmer-Lemmerschau test. We rejected the null when we want to fail to reject the null, suggesting that our model is not specified. So I'll pop out of SPSS for a moment to kind of go over this issue in detail. If you'll recall from last week, I talked about what the Hosmer-Lemmerschau test actually does. So basically it breaks down the sample into different deciles, so like groups of 10% to test if the fit is good for these 10 different subsamples that are of roughly equal size. They can't always be of perfectly equal size if you have like an odd number of participants in your data set, for example. This is the main goodness of fit test for logistic regression. It's basically telling us if our model is properly specified. It's not necessarily connected to explained variance, so it's not telling us about the strength or the predictive validity of the model, but it's talking more so about like the reliability of the model. So a well-fitted model, which is indicated by the Hosmer-Lemeshow test, can still have weak predictive validity and vice versa. If in this Hosmer-Lemeshow test we find that the difference between the observed and expected prediction values is large, it means that our prediction is off. So the more of these errors, the higher the likelihood that we will reject our null hypothesis. If we want to make sure that our model is properly specified, we want to be failing to reject the null hypothesis, meaning that we want our Hosmer-Lemeshow significance test to have as high an alpha value as possible, be as far away from less than 0.05 as possible. What we found in our analysis today, however, is that our Hosmer-Lemeshow test was significant. This suggests that the model is not properly specified. There's nothing in SPSS that's going to tell you why this is the case. It's up to you to understand your data, to understand the research design, your sample, the data collection procedures, to begin to think about why might your model be misspecified. In this case, we have multiple variables that are all measured at the exact same time. So we possibly have an instance where our dependent variable is influencing our independent variable. So for example, perhaps it's the case that individuals that carry guns would instead be maybe recruited by gang members to be involved in the gang. This goes back to like Terence Thornberry's work about selection effects for individuals who might be recruited to a gang because of their propensity for violence. So it's not that an individual was a regular kid and gets recruited by a gang and then becomes violent. It's that their violence brought them into the gang. So we can't use gang membership to predict their violent behavior because it's actually their violent behavior that's predicting gang membership if we're looking at everything at the same time or if we're looking retrospectively. Prospectively, however, is a different matter. What we would want to do is have a lagged relationship between our independent variable and dependent variable. What I mean by this is that we would want to measure our independent variable at what I would refer to as t-1. That's the lag measure. And then our dependent variable measured at time t. So we're essentially looking from wave 1 at time t-1 to wave 2 at time t to see if being a gang member predicted carrying a gun. I didn't do this in this particular analysis because I wanted to kind of demonstrate a Hosmer-Lemeshow issue to you. But you can very easily solve this issue, and in fact, I don't know if I'll have enough time to do it, but if you were to rerun the analysis and you would look at gang membership at wave 1, and then you would look at gun carrying at wave 2, you would find no longer would we have an issue with Hosmer-Lemeshow. We would fail to reject the null hypothesis, meaning that our model would be properly specified. In this case, therefore, all I would need to do is establish temporal order between my independent variables and my dependent variable, but there are other things that we can do as well. Perhaps we have failed to include irrelevant variables, so we should think about whether we have that blue model, what else should we maybe be including? We can check for outliers. That might be another way to address model fit. We can also remove non-significant variables from the model, but I generally am against this approach because if we thought that that variable was theoretically relevant in the first place, then we have a good reason for including it. You might exclude that non-significant variable if you think that maybe we didn't measure it in the right way in the first place, but to me, again, that's all a matter of if you don't think it was measured correctly, why are you putting it in your model to begin with? There's a great saying of like garbage in, garbage out. If you enter garbage, poorly measured variables into your analysis, you're going to get results that are equally garbage. So just don't include those poor variables in your model in the first place. Another thing that you can do is try an interaction term. And the final thing that you can do is to do nothing, because when we have large samples, so for example of 1,000 cases or more, small deviations between observed and expected values in those different sort of subsamples of different deciles, then it's more easily found to be significant. I would still say that try doing different things like establishing temporal order, including other relevant variables, checking for outliers. If none of that works, if you have more than 1,000 cases, you can at least conclude that while I tried to address the issue with Holzmer-Lemerschau, I was unsuccessful. Nevertheless, because I have a relatively large sample size, this might help sort of protect against the misspecification of the model. So I'll actually go through with everyone what we would do to resolve this situation, or actually like how I could resolve it. So one of the ways is to go into regression, back into binary logistic, and I was looking at gun carrying basically at the baseline assessment. But what if I looked at that T-1 rule? So I have my baseline measures would be T-1, and then time T would be gun carrying at the next wave. So here I can take gun carrying at the next wave, the 6-month recall period, hit OK, and let's see if Holzmer-Lemerschau has been resolved. And look at that, it has been. So basically what we just had there was perhaps an issue with temporal order, meaning that our dependent variable was predicting our independent variable and not vice versa as we would have anticipated based on the model. Right? The final thing that we need to do for post-analysis assumptions is what's called the Box-Tidwell transformation test. I lied. There's 2 things that we need to do. The other one is to check for multicollinearity, which again is very, very easy. We would just go into linear regression and we would be looking at all of the same variables. So we're going to be taking our independent variables, throwing them in there, take our gun carrying variable as our DV, and we don't care about any of the relationships between our independents and DVs. We don't have to do that G-1 rule, because really we only care about we're looking at multicollinearity within the variables, not between the IV and DV. So if we go to statistics, and then we can select off collinearity diagnostics. Big one that we're going to be looking at is VIF, and VIF values are not greater than 2, so we're good to go with multicollinearity. We're good to go in the sense that we do not have multicollinearity. The trickier one that we might need to do is a test for linearity, which is looking at whether there's a linear relationship between our independent variable and the log odds of our dependent variable. So we can perform what's called the Box-Tidwell transformation test, and it'll be included in my syntax in Canvas. In this case, we only have one interval level variable, which is the PCLYV. One of the first things that we'll do is conduct a logarithmic transformation. This has to be done for all Box-Tidwell tests. We need to check to see if our PCL score includes 0, and it does. So we would have to add a constant. So we'll add a constant of 0.1. So up to transform, compute variable, and I could just do PCL_ln, and I know that it's ln PCL plus 0.1. If you don't remember ln, just remember that under arithmetic, ln, you can just enter it up there by clicking this arrow and then putting PCL plus 0.1 in brackets. And then we can just hit OK. And we're going to have this new logged PCL variable here. We have to ultimately create an interaction term between our logged PCL variable and our original PCL variable. Option number 1 is just go back into compute variable, and you could do PCL_Box-Tidwell test, or BT, and then we would just multiply PCL by PCL_ln. So that's one option for creating that interaction term that we now have right here. Or we can go into analyze, back into regression, binary logistic regression, and see down here we have this A times B. What this allows us to do is create an interaction term. So we can literally just select PCL underscore log, hold down Control, find our original PCL variable there, and then we can enter it as an interaction term just like that. Plus, we need to include all of the original variables in our model. So what that means is we keep in all of ethnicity, gender, PCL score. So you keep in PCL score and you enter in gang membership as well. I had changed this, so I'll just put it back to our original variable. And then we also have to include the log version of the PCL variable. So we should have basically our original variables would be ethnicity, gender, gang involvement, PCL-YV, our newly created log version of our PCL variable, and our interaction term between the PCL and the log variable, and we hit OK. And what we're hoping for is a non-significant interaction term, which we have right here, suggesting that there's a linear relationship between our independent variable of PCL-YV and the log odds of our dependent variable. And if you're just curious, so remember, keep in mind this exponentiated b value of 1.13. I did the interaction term in logistic regression just by using this function here. But what we could also do is, you'll see, if we entered in that box Tidwell variable that I created by multiplying log PCL by PCL, put it in there, and remember, our exponentiated b value is 1.13. If we hit OK, we get the exact same value. So it's just two ways to get the same thing. So if we had non-linearity, so if we had a significant interaction term, we could try removing outliers and rerunning the box Tidwell test. We could create an interaction term, another interaction term, so we could look at the interaction, for example, between PCL total score and gang membership. We could try a different analytic strategy, which might not be feasible in this case. Or we could do nothing, simply report it as being a limitation and note that the consequence would be an underestimation of the relationship. All right, so you've run your analysis. Here's like the checklist of things that you need to be doing once you have your SPSS output. So before you start thinking about things like model fit or interpreting your odds ratios, you want to address those post-analysis assumptions first. There's no point paying attention to what your odds ratio is for your favorite variable if you haven't made sure that you can actually interpret that odds ratio. Are your assumptions met? If not, then that odds ratio you're trying to interpret is relatively meaningless. So you can check for multicollinearity very easily. All you're going to do is enter your dichotomous dependent variable as the DV in the linear regression analysis, then all your IVs get thrown into the model as well. And then SPSS will produce those correlation fit statistics for you, including variance inflation values or tolerance values, whichever one you actually want to interpret. As I showed in SPSS, to test for the linearity between your interval level independent variables and the logged odds of your dependent variable, you're going to do that box Tidwell transformation. You have to do this with every single interval level independent variable. You don't need to do this with your dichotomous or your categorical independent variables. And the last thing is for outliers, and SPSS will give you that indication of whether or not you have these outliers due to residuals, due to really severe error. And then just as you would with OLS or anything else, you can, for example, remove the outliers and see if you get the same results. If so, you can add the outliers back in and talk about that. If your analysis changes or your output changes in terms of results going from significant to non-significant or vice versa, you can begin to think about, okay, what would be the rationale to justify keeping those outliers in or excluding them? If I got rid of these outliers, how is that going to impact the generalizability of my findings? Once you're ready to interpret your results, you begin to think about whether or not you have a significant model. That's where you're looking at the omnibus test in SPSS. It's just like the F statistic in OLS. It's going to tell you about the overall significance of your model. So you'll want the omnibus test to be significant. On the other hand, you want the Hosmer-Lemeshow test to be non-significant because it will indicate that your model is properly specified. It's indicating to you that there's a lack of discrepancy between observed and expected values when you break down your subsample into those 10 deciles. I need to talk now about pseudo R-squared, and there's a car alarm going off in the background, which I think kind of like appropriately reflects how I feel about pseudo R-squared. My opinion is some reviewers are going to ask for it, so just take Nagelkarki, stick the pseudo R-squared in, and move on. Don't even worry about interpreting whether it is large in magnitude or anything like that. And definitely do not interpret it as explained variance. It has nothing to do with explained variance. Classification accuracy can tell us about the predictive value of our model, but those ROC, AUC values are what I think are really important because they capture both the sensitivity and the specificity of the analysis in the model. Each of those 6 items is talking about the overall value of the model, but very often, especially in criminology, we're interested in specific variables in the model. As I mentioned, I'll take some time at the end of this video to go through odds ratios in more detail. If we have a negative B value, it's going to indicate a decrease in the odds, means that our odds ratio value will be less than 1. In that case, we're either going to do 1 minus our odds ratio or our exponentiated B value, or 1 divided by exponentiated B, depending on whether we want to be looking at the reference category or the group of interest. And always pay attention to confidence intervals. And do not worry about interpreting non-significant odds ratios.
In this next number, I demonstrate the quarter beat tempos. 1-4, 2-4, 3-4, 4-4, 5-4, 6-4, 7-4, 8-4, 9-4, and who for and what for, I don't know. I don't know.
Alright, so for part 2 of this video, we're going to be focusing on multinomial logistic regression analysis. And it's basically taking the exact same concepts as logistic regression, but now we're using a nominal variable. So very clear, not an ordinal level variable. It has to be a categorical variable with 3 or more categories that cannot be rank ordered. We have a separate analysis called ordinal logistic regression that is designed for ordinal level data. Generally speaking, especially with smaller sample sizes, the more categories of your DV that you have, the more trouble you're going to run into. So try to keep your multinomial logistic regression analysis to fewer than 5 categories for your dependent variable, or 5 categories, but definitely not 6. In multinomial logistic regression analysis, whichever category of the dependent variable you're most interested in, I recommend using that category as your reference category. I know it kind of sounds like weird language. We talk about group of interest and reference category, yet the group that we're most interested in this case is now actually our reference group. The reason why is because, let's say we have a nominal variable with 4 categories. In multinomial logistic regression analysis, our reference category, let's say it's group 4, it's going to get compared to group 1, and then it's going to get compared to group 2, and then group 3. If we did not set group 4 as our reference category, and instead, let's say we set group 1 as our reference category, yet we were most interested in group 4, we're going to see how group 4 compares to group 1, but we won't know about the relationship or difference between group 4 and 2 and group 4 and group 3. So figure out which category of your nominal variable you want to learn the most about, and use that one as your reference category. And in SPSS, there's a dialog box that allows us to say what we want the reference category for our dependent variable to be. Unfortunately, we are not able to do the same with our categorical independent variables. We have to manually code them. The assumptions of multinomial logistic regression are very straightforward. They are the exact same as logistic regression, plus kind of 2 or 3 others. First, your dependent variable cannot be a rank, so ordinal logistic regression has to be used if you have an ordinal dependent variable. The second is the independence of irrelevant alternatives test, also known as the Hausman-McFadden test. You can't actually test this in SPSS as far as I can tell. Still don't think it's available in newer versions, but it's typically included in R packages, in Stata, and you should know about it for the exam. But obviously, since SPSS doesn't have it, you don't need to actually run it for your paper. But what you do need to know is what it's trying to say or what it's trying to test.
I don't know.
While this is a statistical test, to me, it's all about thinking conceptually about your dependent variable. Let's say that our dependent variable was referring to modes of transportation. And let's say we had 4 different options. We had car, we had public transport, we had bike, and we had ride-sharing programs. So there's 4 different options there. What the independence of irrelevant alternatives is suggesting is that the removal of a given option would not impact which of the remaining options I might choose. So let's say that I was somebody who consistently drove to work. And so if you removed my option to ride a bike, or removed my option to rideshare or public transport, it would not impact my decision to drive. But let's say that you consistently rode your bike to work. What if you were also told that you were no longer allowed to have the possibility of taking public transportation? And let's say, because we live in Vancouver, especially in the winter, it's raining like 85% of the time. One of the reasons why you ride your bike is because you know that if the weather is bad, you have the option of taking your bike onto public transport, and then you can get home sort of without getting too wet. If I took away this person's ability to have public transportation as an option, then if they were left with the 3 options of ride share, bike, and drive their own car, maybe now they're more likely to drive their own car because they don't have that fallback option of public transport that gave them the confidence to select riding a bike. So this is what we're basically thinking about when we're discussing the independence of irrelevant alternatives assumption. Setting up our data in SPSS is very easy. Dependent variable, once again, needs to have at least 3 or more categories. The last category, aka the category with the highest value, will be set as your reference category by default, but you can change that in the dialog box in SPSS. And sometimes you might even want to play around with your reference categories. It's not p-hacking or anything like that, but you might sort of get a good understanding about the differences across different categories of your dependent variable. When you're running multinomial logistic regression, you're going to have the option to put your independent variables into a factor box or into a covariate box. For the factor box, you can put all categorical variables into this box, but I recommend only putting your non-dichotomous categorical variables in this box. The reason being is that, number one, you cannot pick and choose the reference category. The highest value will always default to the reference category. And we know that when we code dichotomous variables, usually we want 0 to be our reference category. So keep that in mind for a second. When it comes to categorical variables with 3 or more categories, whichever category is the highest is going to be your reference category. So if we had individuals 1 equals white, 2 equals black, and 3 equals Hispanic, but you wanted black to equal your reference category, recode so that white equals 1, Hispanic equals 2, and black equals 3. You could also recode your dichotomous variable, so 0 becomes 1 and 1 becomes 0, or you can just stick that dichotomous variable into the covariate box. And by doing so, you'll be able to leave your reference category as 0 and your group of interest as 1. For all interval level variables, that's going to go into the covariates box. So put dichotomous variables and interval level variables into the covariates box. So now we'll whip through an example of multinomial logistic regression analysis using SPSS. And I didn't really like the pathways assistance study data when it came to multinomial logistic regression, because there weren't that many DVs that were nominal, that were more than 2 categories. So I'm using my own data here from the Incarcerated Serious and Violent Young Offender Study. Alright, so we'll finish off today's class by going through an example of multinomial logistic regression. I'm going to be looking at the prediction of offending trajectories from participants from the Incarcerated Serious and Violent Young Offender Study. So you're looking at a trajectory analysis here. It's conducted through an analysis called semi-parametric group-based modeling, and it's done usually in SAS or Stata, so you can't actually do this in SPSS. What we see along the x-axis is age, and along the y-axis, the number of convictions. SPGM estimates these different trajectory groups, and then individuals can be assigned to these trajectory groups based on posterior probabilities and sort of the odds of correct classification. So is this a nominal variable, or would it count as an ordinal variable? Typically in the literature, they'll argue that, for example, we cannot rank these trajectories. We have this trajectory here that is lower than this trajectory here, but over time, this trajectory has a higher rate of offending than this trajectory. And so we could say that maybe we don't have these ordered categories of trajectories, but it would all kind of depend on what your analysis produces. So we're going to use this as our dependent variable when examining multinomial logistic regression. So I'll flip over to my multinomial logistic regression example here using data from the Incarcerated Serious and Violent Young Offender Study. I like to do things like remind myself in the label what I want my reference category to be. So here we have low rate, early onset, slow desistance, AL is 3 or adolescence limited, early onset fast assistance is 4, and 5 is high rate chronic. So low rate was this one here, adolescence limited was this one here, and this one definitely looks like it is the lowest rate offending trajectory, even lower than the low rate trajectory in the sample. So that's how I decided that I wanted it to be my reference category, and its value is 3, so it's my reminder here to set the value to 3. Then I have several different independent variables. K-file indicates whether the individual has had a history of perpetrating intimate partner violence or family violence. Fed is whether they've ever been sent to federal custody. FA offender is if they've ever been involved in a firearm offense. ASO is if they have a history of sex offending in adulthood. Gender in this case is just a dichotomous variable, whether the or actually technically we did have participants in the sample that self-reported being transgender, but they weren't included in this particular analysis. We're just looking at males participants compared to female participants. Up to this point, these are all dichotomous variables. Conviction age of onset is an interval level variable. And I'll start just by looking at ethnicity underscore RC, where we have 3 different ethnic groups: indigenous participants, white participants, and participants that self-reported being part of a non-indigenous minority group. So we can begin to run our analysis by going up to Analyze, Regression, and we're just going to select Multinomial Logistic Regression. And obviously our dependent variable is going to be our offending trajectories. We set it here, and then we can select our reference category, and you could do the first category. It defaults to the last category, but in this case I want a custom value. I want that value to be 3, and I can hit continue. And then for our factor box, we could technically include all categorical variables. Sometimes I like to include my dichotomous independent variables in as covariates. When I do so, it means that I want the first category to be my reference category. So I want my 0 to be my reference category. So in this case, I want for K-file, federal custody, firearm offender, and history of adult sex offending, I want my first category, aka no, to be my reference category. So I can place them into the covariate box here. In this case, I'm just going to put gender, even though it's going to be dichotomous in this instance. I want my last category, which is female participant, to be my reference category. So female participant equals 2, male participant equals 1. I want female participants to be my reference category, so I'll put it up here. And then I can put my ethnicity variable up here. And this ethnicity variable, again, just like the other one, is going to make the reference category the last category. So in this case, 3 equaled that non-indigenous minority group. So that's what our reference category will be. What we're most interested in is the statistics dialog box. Automatically, SPSS will check off these as defaults. Don't bother to uncheck them. But there are a couple things that we want to check off. One is classification table. That's just the same as the logistic regression analysis. And then we need to select the goodness of fit test as well. Now we're okay to go. We can hit continue. And you don't need to select anything from options, saves, or criteria. We can literally just hit OK. Coming out of SPSS, quickly running through model fit, it's like almost identical to logistic regression analysis. You might like it more because you actually aren't able to and therefore don't have to run your AUC values. But we're going to be looking first at the likelihood ratio test. It's basically like the omnibus test in logistic regression. We are looking to reject the null hypothesis here. We've got that same old goodness of fit test that was like the Hosmer-Lemmerschau test in logistic regression, and we want to fail to reject the null hypothesis there. The deviance goodness of fit is what you would report in your papers and in your assignments. You know how I feel about pseudo R-squared, and then you've got your classification tables. It's just like in logistic regression analysis that are going to tell you about how well it predicts your different categories of your dependent variable. If it's strong or not, it's kind of all dependent on theory or prior research. There are no benchmarks. It's all about what would you have maybe expected based on past literature. What you see up here is a warning sign. Just going to talk about when you have, for example, missing data. First thing we want to look at is our model fit information. This is like our omnibus test with logistic regression, and so we want this test to be significant. So that's good. The next thing that we look at is our goodness of fit test, which is kind of the equivalent of the Hosmer-Lemmerschau test in logistic regression. And so to pass this assumption, we want to fail to reject the null hypothesis. And we do in this case, because P is 0.05 or greater. In this case, it's quite high, so we're good to go there. We have our pseudo R-squared values. It defaults to giving you these different 3. You could just Nagelkirky it, talk about that, and you know how I feel about this. The last thing that we can look at in terms of model fit, and I don't know why, but it spews it out at the end of the data set, is your classification table. Remember, in logistic regression, this was part of model fit, and it would tell us this before we got to any of our particular variables. So if you have a look here, you can see that our ability to predict the early onset fast desistor group absolutely sucks. It's garbage. We're not doing a very good job with prediction. Our overall model is significant, but something to keep in mind is that we're not being very efficient at predicting the early onset fast assistance trajectory. When we're looking at parameter estimates, or when we're looking at the individual independent variables in our analysis, we're going to have separate boxes in our SPSS output for each category of the dependent variable, except for the variable that we set as our reference category. So each category of our dependent variable is going to be comparing against our reference group of that dependent variable. The leftmost column clarifies which category we're actually looking at for the dependent variable. And ultimately, just like in logistic regression, here we're interested in our exponentiated b values or our odds ratios, and we're looking for that 95% confidence interval, because if it's especially wide, then all we know is that that odds ratio that we're getting is probably not the true odds ratio. Remember, at the very beginning of the class, I said that the one thing that we know about these coefficients is that it's not the true value. How we interpret these odds ratios is exactly the same as in logistic regression analysis. The next thing that we can look at are our parameter estimates that are going to be telling us about individual variables in the model. And our interpretation is exactly like logistic regression. It's completely identical. It's just now that we have multiple categories to compare our reference group to. So before it was just a dichotomous variable, so we had one group of interest and our reference category. Here we have our low rate group compared to our adolescence limited group, our early onset slow desistance group to our reference group, and so on and so on. So I want to point out some major issues with this analysis. This is what I was talking about when referring to extremely large confidence intervals. So here, firearm offender. What can we say here? Well, if somebody was a firearm offender, they had like 165 billion increase in the odds of being in the low rate trajectory compared to the reference group of adolescence limited. This obviously is not the case. We've clearly included a variable that we shouldn't have. That's why we had up here this warning sign about the Hessian matrix. If we take a look here, if we do a little descriptive statistics, we can see that only 2.7% of our sample had endorsed or had been involved in a firearm related offense. So only 11 individuals. Now remember the assumption of multinomial logistic regression being small cell counts. So imagine this. We have 11 individuals that have been involved in a firearm offense, but we also have 5 categories of our dependent variable. We have low rate, slow desistance, fast desistance, high rate chronic, and our reference category of adolescence limited. So effectively, the problem that we have here is that if we presumed an equal distribution, we would have about 2.1 cases in each trajectory. And so, thinking back to like chi-square analysis, what you know about small counts as a violation of an assumption, we clearly have that issue here. The solution would be to simply remove the variable from the analysis, which is what we're going to do now. Very simple, just back in here, we can take out that firearm offense, voila, and we're back. Now we can see that that Hessian warning is gone, and we don't have any inordinately high odds ratios in our model. We still have some that are high, like look at federal custody. I would be hesitant to interpret this as like individuals in federal custody were 10 times more likely to be in the low rate group compared to the adolescence limited group, because look at the upper bound and the lower bound. We have these very wide discrepancies, and so I would not be particularly confident in saying that this is a large effect size. When it comes to our nominal variables of 3 or more categories, notice here that ethnicity equals 3 is blank. This is telling you that that's our reference category. So when ethnicity equaled 1, that was, we can flip back here, ethnicity 1 is indigenous. So here, ethnicity equals 1 indigenous. We're comparing it to individuals who are a non-indigenous minority group. And we can see that it's not significant, so we wouldn't bother with interpretation. However, here we can see that it is significant. So we can see that indigenous persons were 9.73 times more likely to be in the slow desistance trajectory compared to the adolescence limited trajectory when compared against non-indigenous minority persons. Let's find an odds ratio that's less than 1, because I want to go through the interpretation here, because I think it's a little bit more difficult than when you have an odds ratio that's 1 or greater. Normally we wouldn't be interpreting this variable because it's not significant, but just for the sake of argument, let's say it was significant. So adult sex offense, it's less than 1. So we can automatically know that individuals that committed an adult sex offense would be less likely to be in the low rate group compared to the adolescence limited group. But how would we actually interpret this as an odds ratio? So again, we could just pull up our calculator. And one of the options we have is to do 1 minus 0.778, gives us a value of 0.22. So we could say that individuals with a history of adult sex offending were 22.2% less likely than individuals with a history of not sex offending as an adult. I don't know why I said that so weird, not sexually offending. We're 22.2% less likely to be in the low rate trajectory compared to the adolescence limited trajectory. Another way that we could interpret it is just doing 1 divided by 0.778. And instead of adult sex offending being our group of interest, it becomes our reference category. So now we would say that individuals without a history of adult sex offending were 1.29 times more likely to be in the low rate trajectory versus the adolescence limited trajectory compared to individuals with a history of sex offending in adulthood. Here's where I think students can often go wrong. Remember which reference category you're changing. You are not changing the reference category of your dependent variable. You're not switching low rate as now becoming the reference category and adolescence limited becoming the group of interest. Whenever you do this transformation, you're changing the reference category for your independent variable and not your dependent variable. So I'm not going to go through all of the assumptions of multinomial logistic regression analysis because they're just the same as those associated with logistic regression analysis. But some of the tests that you would have to do can't be done in multinomial logistic regression. So what you would have to do is you would have to run multiple logistic regression analyses, where you'd be having one regression analysis where it's low rate individuals compared to adolescence limited only, another where it's the slow desistance compared to the adolescence limited, and FD adolescence limited, RC adolescence limited. If that's not clear, we can talk about it in the synchronous portion of the class. Okay, so in terms of summarizing what we need to do for multinomial logistic regression analysis, first, again, we have our assumption checks. And then when it comes to diagnostics and model fit, unlike logistic regression, where there are a lot of different statistics for performing model diagnostics, it's not as straightforward to do these diagnoses in multinomial logistic regression analysis. So instead, what you have to do is run separate logistic regression analyses where you're comparing your reference category to each of those other groups of interest for the other categories of your dependent variable. When it comes to multicollinearity though, you can just do the exact same thing, just run OLS, because remember, multicollinearity doesn't care about the nature of your dependent variable. It's all about your interval level independent variables. When you're looking at linearity between your interval variables and the log odds of the DV, you can once again do that Box-Tidwell transformation. Outliers require you to do those separate logistic regression analyses that I referred to, and small cells, which you're going to probably see a hint of if you have really wide confidence intervals. Small cells are referring to like if you have very few individuals who are like a yes on your independent variable of interest and are a yes on your reference category of interest. Like logistic regression, once you've passed the assumption checks or addressed your assumptions, then you can move on to interpreting model fit. When you're looking at the significant model, you can look at that -2 log likelihood value in SPSS. You want to be rejecting the null hypothesis. Same thing when we're looking at the likelihood ratio test. But then when we're checking for the goodness of fit test, we want to, like Hosmer-Lemershell, fail to reject the null hypothesis. We also have our pseudo R-squared and our classification accuracy. Then we can move on to the interpretation of specific independent variables in the model. Values with a negative b, just like in logistic regression, indicate a decrease in the odds. But as I mentioned as well, these b values are talking about the log odds. It's more interpretable to look at the exponentiated b, or our odds ratios. And if we have an odds ratio that's less than 1, we can either do 1 minus the odds ratio or 1 divided by the odds ratio. Okay, so I will end with a review of how we go about interpreting odds ratios. In total, there are 4 different scenarios that we need to think about. We need to think about how we interpret an interval level independent variable when the odds ratio is 1 or greater, how we interpret an interval level variable when the odds ratio is less than 1, and then the same scenarios but when we have a categorical variable, and it doesn't matter if it's dichotomous or more than 2 categories. So that's everything that I wanted to do in SPSS with multinomial logistic regression. Again, I'm going to just throw in, it's not going to be a very nicely edited video because I've had MediaSite crap out on me so many times and I'm so frustrated. I'm up at school on Saturday right now because MediaSite wasn't working at home on Friday and I recorded this and then the thing disappeared. So apologies for the low quality of the video, but the message is what's important, the idea of how to interpret odds ratios in multinomial logistic regression. So that's everything. Have a good rest of the week. Hopefully this was helpful, and take care, everybody. Alright, hi everyone. I'm going to go over how we can go about interpreting odds ratios. So I've put together a quick little PowerPoint presentation here that is going to show us basically 4 different ways that we go about interpreting odds ratios. So we can interpret an odds ratio when it's greater than or equal to 1, or when it's less than 1. And how we do this can also vary depending on whether the variable is interval or dichotomous. So when I say dichotomous, I'm also including any type of categorical variable here. It's just that ultimately when we're interpreting a categorical variable, let's say it's 4 or more categories, in the logistic regression or multinomial regression, even if it's 4 categories, we're ultimately only comparing 2 categories. So we've got our reference category and our group of interest. We might be comparing, if our reference category is indigenous, we can compare white to indigenous and non-indigenous minority group or another black, Hispanic, etc. to indigenous. So we have essentially a categorical variable that we treat as a dichotomous variable. So let's take a look at how we go about interpreting interval level variables. So first at the top, I'll show you an example of what we do when we have an odds ratio that is greater than or equal to 1, and how we would go about interpreting this. So I'll pick up my pen here. So here we're looking at age of onset, and we're looking at the low rate trajectory as the group of interest for our dependent variable, and our reference category for our dependent variable is the adolescent limited offending trajectory. So what I saw from assignments was that students were often reporting or looking at B coefficient, or the log odds, or the Wald coefficient. Don't worry about either of these for the purposes of the term paper or the final exam. What you're interested in is exponentiated B, which is also the exact same thing as an odds ratio. So you're interested in this, you're interested in whether it is significant, and then you would like to look at, for example, the lower and upper bound of the confidence interval to see how accurate that odds ratio likely is, or whether that odds ratio you feel comfortable saying. For example, if we look at federal custody, individuals who have been in federal custody are 11 times more likely to be in the low rate trajectory compared to the AL trajectory. Yet the confidence interval ranges from 1 to 90. So we're not very confident that 11 is definitely the value. We know that it's significant, but we don't know that the odds is definitely 11. So we just want to be a little bit cautious there. It's still okay to interpret, it's still okay to report the odds ratio, but we want to be cautious about how much weight we assign to that definite value. So let's actually now look at what we came here to do, which is to interpret an interval level variable. So we've got age of onset, and we've got the odds ratio, or exponentiated b, as being greater than 1. So it's very straightforward. Just like with OLS or any interval level variable, we'll talk about a 1 unit increase in age of onset is associated with a 102% increase in the odds of membership in the low rate trajectory compared to the reference category, which is the AL trajectory. Where things get a little bit more complex is when we have an odds ratio that's less than 1, which is the case here when looking at the early onset fast desistor trajectory. So in this case, we can interpret it in one of two ways. We can sort of keep in line with the traditional OLS approach of interval level variables. So we would say that a 1 unit increase in age of onset is associated with and then here's where we have to recalculate the odds ratio. This 0.693 value means nothing to us. If we have an odds ratio of less than 1, that less than 1, we can't actually interpret it as an odds in and of itself. We have to do 1 minus 0.69, and that would give us a value of 0.31, or a 31% decrease in the odds of membership in the EOFD trajectory compared to the AL trajectory. So in this case, we're showing in what way does the variable decrease the likelihood of being in the EOFD trajectory compared to the AL trajectory. But what if we were really interested in understanding how the variable increased the likelihood of being in the EOFD trajectory compared to the AL trajectory? We would have to calculate the odds ratio slightly differently. So at the bottom here, we would say a 1 unit decrease in age at first conviction. So this decrease is different. Before we were looking at increases in age. A 1 unit decrease in age is associated with, and instead of doing 1 minus, we do 1 divided by. So 1 divided by 0.69 means that we're seeing a 145%, and here's where it differs again, increase in odds of membership in the EOFD trajectory compared to the AL trajectory. So now we've changed the direction that we're looking at for the IV. Instead of looking at increases, we're looking at decreases. And that's allowed us to interpret in what way does this particular variable increase the likelihood of being in the EOFD trajectory compared to the AL trajectory. My personal preference is always to use the first approach that I talked about. I think that it's more straightforward. We're just talking about decreasing the likelihood. So that's that for interval level variables. What about for dichotomous variables or categorical variables that we're going to be interpreting sort of in a dichotomous way because it's group 1 versus group 2? So in this case, we've got the exact same output as I showed earlier. We have ethnicity equals 1, and in this case 1 equals indigenous, 2 equals white, and 3 equals a non-indigenous minority person. In this case, we've let 3, the last category, equal our reference category. So the non-indigenous minority group is the reference category to which indigenous persons and white persons are being compared. So looking at ethnicity 2, this would be our individuals that self-reported being white. We have an odds ratio that's greater than 1 or equal to 1. So when we will follow the guidelines up here, we would say that when compared to non-indigenous minority individuals, that's our reference category, white individuals are 1.15 times more likely to be in the low rate trajectory group compared to our reference category, which is the AL trajectory group. We could also say 115%. So 1.15, the equivalent is 115%. So again, nice and straightforward. But when our odds ratio is less than 1, as is the case here. Again, we can't just straight up interpret that odds ratio. We have to transform it. So we can keep our reference category the same. We can say compared to non-Indigenous minority individuals, white individuals are 1 minus 0.98 is 0.02, or 2% less likely to be in the EUFD trajectory compared to the AL trajectory. So we're keeping our reference category for our independent variable the same. We're just talking about a lower likelihood of being in the EUFD trajectory compared to the AL trajectory. Now, we could be more interested in which ethnic group is associated with an increased likelihood of being in the EUFD trajectory compared to the AL trajectory. So here's where we have to change, not the direction. So recall when we were looking at independent variables, we would talk about changing the unit direction, thinking about increase, 1 unit increase. Now we're looking at a 1 unit decrease. For these dichotomous or categorical variables, we now change our reference category. So you can see here we've now changed white becomes our reference category. So 2 equals white. It was our group of interest. Now it's our reference category. Compared to white individuals, non-Indigenous minority individuals are 1 divided by 0.98 equals 102% more likely to be in the EUFD trajectory compared to the AL trajectory. So we're always keeping our dependent variable, reference category, and group of interest the same. We're only changing the reference category for our independent variable. So in this case, I've been interpreting odds ratios that are not significant. I'm only doing this because it worked out in terms of finding a odds ratio that had a value that was less than 1. So that's why I'm doing this. For the purposes of your paper, you only need to be talking about and interpreting more fully your variables or your odds ratios that are significant at p less than 0.05. So I think that will be a little bit more straightforward. I'll post this, and then if you have any additional questions, feel free to reach out and ask them.